Russian or English?
Ну, наверное, лучше по-английски.
Okay, then, yeah, great. Then I'll take an opportunity to practice my English. Rare opportunity nowadays.
Чем хуже ваш английский, тем больше вы понятие основное выражение.
Okay, I'll start from writing down a plan. A plan will be non-linear. So my main goal here is to work out a simple model, a very simple model, where I can solve Heisenberg equations explicitly. The good thing about this is that I believe this can be done in an hour or maybe less, and it is almost elementary. The downside is that as it is almost elementary, some of the results can be obtained by other methods, more well known. However, I will argue that this is not a downside of the method, but just a feature of this specific model. So first I will give a short recap of what quantum dynamics is. Probably I should.
Чуть-чуть опустить, как бы, в принципе, она есть.
Then I will introduce my simple XX model. I will write down Heisenberg equations for a subset of operators there.
Heisenberg equations in the conventional sense of quantum mechanics.
Right. And I will solve them. I will solve them, and moreover, I will find some explicit formula for expectation values of some observable after a quantum correction. At this point, my quantum model will be a closed model described by a Hamiltonian. I have already delivered actually several talks on this topic. One of them was in November 2021. I will assume that you remember nothing about that. However, for those who remember anything or who have listened to my talks elsewhere, then the next step will be completely new. This is open system dynamics. First, I will give again a brief recap of what this dynamics is. Remind a Lindblad equation. And then I will consider two sorts of open XX model with two different types of dissipation. Sigma Z dissipation and sigma X Y dissipation, and I will explain what this means. Okay. This is a linear part of my plan, and I hope I will manage to do that. Now there are different branches from this plan that I plan to cover if time allows after I'm done with this stuff. First,
What do you mean by all consistent?
right. I mean, this is just a plan.
I would ask maybe a simpler question. What is your main aim? So what would you like to achieve?
Yeah, my message is to introduce an old but underestimated method of solving coupled Heisenberg equations for integrable and even non-integrable systems.
So first you just described to us the case when these Heisenberg equations can be solved,
Right.
and then you turn to the case when they cannot be solved, yeah?
I
You have to replace them by something else.
I will not go into that into detail, but I will mention it in the end. So actually this is one of motivations for me personally to do this integral stuff, because it sheds light on non-integral stuff. Okay, now branching. This XX model can be solved actually by Fermatization. And I will explain why when Heisenberg equations can be solved in the original spin representation, this should be done. Why this is? So I'll try to convince you that Fermatization is not as good as solving Heisenberg equations directly. Then I'll probably mention Onsager algebra and n-state Potts models. These models are also integrable, but not mappable to free non-fraction fermions, but they can be solved by this method with essentially the same effort. So this is one of motivations why we prefer Heisenberg equations to Fermatization. Now, here, as I already mentioned, I'll just make a short comment on how the results in this integrable case, exactly solvable case actually, not integrable, exactly solvable case shed light on general dynamics with dissipation.
I think it is time for a definition.
Hmm?
I think it's time to give some definition and some results. The plan is clear enough.
No. I'm writing this plan down in order when you try to ask me questions, if they divert me from this linear part of the plan, I will just skip them to the end. And finally, I will discuss a mapping between Lindbladians and non-Hermitian Hamiltonians, and what we can learn from these solutions in view of this method. Okay, that's all with the plan. Now, a brief recap of quantum dynamics. In quantum mechanics, here in the first part of the talk we are talking about closed quantum systems. Closed quantum systems are described by Hamiltonian H, which is an operator on a Hilbert space, and for all practical purposes and for at least in this talk, we can assume that our Hilbert space is just C power 2n, where n is the size of the system, or more explicitly, the number of spins 1/2. This is a self-adjoining array.
I'm sure you don't want to see to the end.
Why this 2 to power n? Because this is a Hilbert space of n spins 1.
You see to the end.
Чому це в степені 2, це в степені? Да? А є?
Because
По-моему, Рома хочет, чтобы вы написали C2 в степени n, да? Ром, в стандартной степени или вы...
Да.
like this.
Ну или два в степени n можно написать. В смысле, там все-таки не просто c в степени 2n, а c в степени 2 в степени n. Вот так вот.
Нет, это уж слишком, вы что? С2 тензорно n раз.
Да, согласен.
Это не 2 степени.
Или так.
Okay.
Еще цену какую?
Okay, I think everyone in this audience understands what I mean. Now we have an observable, and in the Schrödinger picture, the observable corresponds to some operator O. And we have a time evolving state. In general, it is a mixed state, rho t. And the initial state, rho 0. It evolves according to the Schrödinger equation, which reads false. And it has a formal solution
Может быть, вы возьмете белый мел?
I don't have a white chalk, so there is no.
Проблема даже с мелом уже.
Все
I can try to choose one which is more visible.
Red is more visible.
Okay, the pink one is better. Great. So the expectation value of the observable, the thing which we measure in experiment, then is given by a trace of this rho t. What you see in this line is what is known as Schrödinger picture. There is an equivalent picture named Heisenberg picture, and it actually follows from this equation, from this equation. So we can write it as trace. Thank you very much. Rho 0 e or ht o ht. This is called Heisenberg operator t o at t. So I bring your attention to my notations. Whenever I have t here, a lower index t, then I mean that this is an operator in the Heisenberg picture. When there is no t, I mean that this is an operator in Schrödinger picture. So this is Heisenberg. And now the equation of motion is an equation of motion of Heisenberg operators, and it reads d over t equal I h of t. Now a technical remark is that this O t, I remind that it is nothing else that a unitary rotated Schrödinger operator and since this unitary commutes with h trivially, so this is e h2 So this may look like a tautological formula at the first glance, but what I want to convey here is that in practice, when we want to write down a Heisenberg equation, we take a commutator between the Hamiltonian and the operator in the Schrödinger representation, and then declare that what we obtain here is again a Heisenberg operator. This will be clearly more clear when I turn to a specific example, and this is what I'm going to do.
Just maybe part of the question, what
Yeah.
you call by solution to Heisenberg equation? Because in a sense, you wrote down a solution.
Yeah, this is a formal solution. This one is formal solution, and in many body systems, it is always useless. What we call, that's a good question, I'll write it down right now. So we have an operator, a Heisenberg operator, and if we can expand it in Schrödinger operators, explicitly known Schrödinger operators, and this with these explicitly known time-dependent coefficients, then we say that we have solved the Heisenberg equation. Okay?
And not the power,
No, it's just an index.
so it's better than to write it down.
Now I'll need this down for T. Yeah. So you'll have to accept this notation. There will be a lot of upward. So,
Можно скобочки взять.
Ну еще же все-таки статус этого всего, вот сумма там какая-то, она конечная, бесконечная, что это за операторы. То есть как бы вы сказали пока что решили, когда всю зависимость от t забили функции. Да?
right. So I'm going to find explicitly these operators and these functions. Okay. This was the first point of contact.
So this is what you call by quantum dynamics.
Right. This is just the statement of the problem, what I'm doing. Now, a specific Hamiltonian I'm going to consider is the Hamiltonian of the XX model, which is written by physicists like follows. These sigma x, sigma y are Pauli matrices. There is also sigma z Pauli matrix. This J labels the site or the spin in the spin chain. In total, there are n spins. We assume periodic boundary conditions.
How do you stick to that it acts on?
Sorry.
So I just said, mathematically, means the copy of feature that it acts on.
Maybe the question is about the mathematical meaning of this formula. I'll say it in a moment. Okay, so mathematically say sigma x5, sigma x6 means that we have a tensor product of 4 unity matrices. Then at side 5 we have sigma x, at side 6 we have sigma x, and then we have a lot of unit matrices.
Maybe also a question was, I was recognized what Rom asked, so about n plus 1, who is n plus 1?
N plus 1 is 1. So n plus 1 is 1. This is called periodic boundary conditions. Okay. Now, assume we wish to boldly write down Heisenberg equation, say for the operator sigma x1, sigma x2. This is our operation. So dt ot would be, we have to take a commutator between the Hamiltonian and this guy, and what we get, it commutes with all these terms, but it doesn't commute with two of these terms, and what we get is something like sigma x, sigma z, sigma x, here goes n 1, 2 plus sigma x, sigma z, sigma x. Now, sigma y. Here is also sigma y. 1.
So I'm a bit lost. So what are you writing down?
I
You took this particular operator. Yeah?
I commute the Hamiltonian with this particular operator. So, right. One, two, three, and here goes n 1, 2, and here goes 2, and maybe plus or minus. Forgive me the sign. Okay.
Why you write down this is dt ot?
Because
then you're
because this is the Heisenberg equation.
yeah, but it's at the moment t, but you were commuting Hamiltonian and all t equals to 0, right?
Right. This is what I tried to convey in this slide. So we
Yeah, and then by these brackets with t, you mean that you then apply this
unit rotation, right?
unit rotation.
Exactly. Exactly. We see that we have expressed the derivative of one operator through the derivative of a different operator. Now, if we act boldly, we just take a derivative of this operator and obtain something else, and further and further and further. And this is how we get a chain of Heisenberg equations, coupled Heisenberg equations. It is not hard to see that in this particular case, if we start from this operator with this Hamiltonian, we will get very particular forms of operators here. They will look like sigma. The first one will be either sigma x or sigma y. Then we will have a strings of sigma z's. And then we'll again have sigma x or y. And these are consecutive indices. So this is j, this is j plus 1, this is j plus 2, and so on and so forth. This is j plus m minus 1, j plus m.
Maybe it's better to write yx on the last sigma, because when we have
No, if we commute this one again with the commutator, we'll get sigma y, sigma z, sigma z, sigma y, and sigma x, sigma z, sigma z, sigma x.
And what for you need these chains? What for you need these chains?
These chains emerge when we try to boldly write down Heisenberg equations with this initial operator. You will never obtain, for example, an operator like sigma z, j, sigma x, j 1 sigma z j plus 2. Never. You will never obtain an operator like sigma x j sigma y j plus 2 with a unit operator in between. So the idea is that you get not the whole space of operators in this space of operators, but you get very specific ones. In fact, their number is linear in the system size, and this already tells you that the complexity of the problem is reduced to what you could expect generally. Now, let me formalize this observation and introduce some formal, some algebra operators. So we introduce the operator A0, which is all the operators I'm going to deal with here are translation invariant. The Hamiltonian is translation invariant, and all the operators I'm going to deal with from now are translation invariant. So everywhere you will see these sums. This is Z, and this is just the polarization along the Z axis. Now A n equal to sigma x j product of sigma z's j plus I, where I goes from 1 to n minus 1 times sigma x j plus n. This is for n greater or equal than 1. A minus 1 is obtained from A1 by changing x x to y. So A for negative indices, an is just the same guy, but here goes sigma y and here goes sigma y. And also we introduce En, which is a similar thing. Here goes sigma x. And here goes sigma y. And this is for n greater than
The last slide is again G plus 1.
right. J plus 1. For negative indices, we just replace x by y and y by x. So it starts from sigma xy and ends by starts from sigma y and ends by sigma x. B0 is just 0 by definition. Now we introduce operators Hn that are just 1/2 An plus A minus n. In particular, H1 is just our Hamiltonian. And it is an easy exercise to see that all these guys commute one with each other. Hn equal to 0, so these are integrals of motion. There is a different family of integrals of motion. A similar one. And they also commute with one another and with, sorry, Q.
Yes.
0.
Zero.
Thank you. And we need more linear combinations. This one is. And this one is I over 2 B and this imaginary unit is for historical reasons, and if I manage to reach this story about Heisenberg algebra, I will tell you why it is here. In general.
It should be an index.
Sorry?
It should be an upper index, right?
Right. Thank you.
Maybe question. If I perform like 2 to 3 terminal from geometrically,
Yeah.
I mean that all those components are quadratic terminals.
Exactly.
There's some.
Yeah, exactly. Thank you very much.
All of
This is the downside of this model that, but you'll see that even though they're quadratic, it's not easy to perform certain tasks with even these quadratic elements. Okay.
Quadratic means that they're all diagonalized in
Like
Fermionic basis.
psi
Yes.
dt to some power psi.
So they're diagonal Fermionic
Yes.
basis.
Not necessarily psi dagger, psi maybe psi
Psi
psi.
dagger d to some power psi.
So they are quadratic. That's it. Now I'll go with this blackboard.
And what happened for big
What happened to?
for n greater than bigger?
That's a good question. There are special expressions for all these guys for n equal to n large. There are two ways to deal with that. The first one is a straightforward one is to pedantically keep the system size finite and write down these special expressions for these operators for n equal to n capital and proceed in this way. This is straightforward but somewhat bulky. Another way is to work in the thermodynamic limit from the outset, and this works fine, and it just looks more elegant and the results are the same. So I'll skip these special expressions for any capital. We are actually almost reached the midpoint of my linear part of the plan. We need 2 more linear combinations. Sorry, xn, which is mn plus gn, and yn, which is mn minus gn. And one can check that the Heisenberg equation for xn looks in this simple form. And for yn looks in this simple form. So you see that we have reduced many body problem essentially to a single particle problem of a hopping of a particle on a line. This equation can be easily solved as your
Sorry,
yeah.
These x's, m, g, and x's, they do not commute with Hamiltonian.
They don't commute.
Only these charges.
Right.
Yeah.
Right.
So then, when you write down these Heisenberg equations, it's at the moment t, or where is?
Sorry.
So everything is at the moment t.
Right.
Okay. So now, where are particles?
No, I mean.
No particles up to now, yeah?
Hmm?
No particles.
No particles. Just it's solving this equation is equivalent to solving a quantum mechanical problem of a single particle hopping on a line with nearest neighbor hopping matrix elements. In this sense, so we have reduced an initial problem to a hopping problem in the space of operators, and this space of operators is greatly reduced with respect to the whole space of operators. Okay?
Скажите, все-таки, что это за проблема с частицей? Я просто не вижу никакого.
Okay.
Где тут частица?
Let me.
Волновая функция частицы,
Yes.
тогда она будет скакать.
Exactly. If x were not an operator but wave function, then you'll get just
Ну что, слышишь, она прыгает на шаг вправо, на шаг влево.
exactly. Right.
И какая радость от этого?
Because, well, the good thing about that is that this problem can be easily solved. As I have already written, we are interested in the solution in the sense that we I will here use a calligraphic G, not to be confused with this G. So we want to expand our Heisenberg equation in series in some Schrödinger operators with some explicitly known time-dependent coefficients. Now, then this equation is equivalent to the equation like dt over matrix G m. This is the matrix of this equation, linear equation, and also
This M is a three-diagonal infinite matrix. Yeah?
exactly, yes. If you don't like infinite matrix, you just take finite system size, it becomes three-diagonal finite matrix, you solve this equation and you take them to linear. Okay.
But if you reduce it to finite space, it won't be three-diagonal, it will also get the non-vanishing elements of the corners. Yeah?
Right. No, it will still be three-diagonal, but the
Это как у Тода, но если у вас лакс в Тоде трехдиагональный, но если вы периодическую задачу решаете на n сайтах, то у вас появится в правом верхнем и в нижнем левом углу ненулевые элементы. Ну, из-за того, что m плюс 1 равно 1.
no, this is not the same cases here, but we can discuss it. It's not essential. Anyway, it can be solved in both cases. Now, this calligraphic G is nothing but a propagator. In this case, I will not bother you about. I write this down for future purposes. I will not bother you about solving this linear system. I just write down the solution. Assume you can believe that the solution can be obtained. So this x t is some n1 infinity integral p over to p L to p to pi, right? Thank you.
Какая-то мода это оператор. Понимаем мода какая-то? Первая и минус первая.
There is
Looks like basic function.
right, we'll get the Bessel function. At the moment, it's not the Bessel function because it is an operator, and you have to sum m. You mean?
I mean,
yeah,
the coefficient.
the integral is the Bessel function, right? So the whole expression is the sum of xm's with Bessel functions. That's true. Okay, this is an explicit.
Может, ты даже скажешь, какая?
Ну, там типа n плюс m, но с нами. Или n минус.
You'll see in a moment.
Типа.
Yeah, you'll see in a moment.
Они же разные. J.
Ну, прям J, прям J.
А, прям 10, ну как прям 10, да?
Now we have got an explicit formula for an Heisenberg operator, but now I would like to make the things even more explicit and calculate the expectation value of this operator for a particular initial condition. Yes, the initial condition will take rho 0, which is just a projection operator, so it is a pure state. It is a projection operator on psi 0, and psi 0 is just a state where all spins are aligned along x direction. So this means that trace rho 0 sigma x j is always 1. And trace rho 0 sigma y z j is always 0 for any j.
Почему надо по этому состоянию Why you want this particular state?
Because I want to obtain some specific expression, just formula. And on the one side it is a simple state, it will easily deal with the sum. On the other side, if you, okay, this question diverts me from my, I'll address it if I have time in there. Now from this we can easily see that a Schrödinger operator m, xm is non-zero only when m equal to 1. So it is simply L when m is equal to 1 and 0 otherwise.
Може зараз.
This means that we have only one, when we calculate the expectation value of this observable, then we get a single term in this sum. And then we get indeed just an integral which a Bessel function, it is something like this. L over 2, J0 t plus j 2 alpha t. So this is an explicit answer.
So, did you explain that's why x average of x is non-zero only for the first round?
Because you have 0 as soon as you have.
Because I have always.
Yeah. And x1 is the only operator that contains only
Which is just
sigma.
What is the
L, sorry, and it's the total number of spins. Okay, I'm done with the first part of my linear part of the plan. I'm done with, we have obtained a solution for Heisenberg equation for our operators x, y, and we can find everything else by just forming linear algebra. Now, how much time do I have? Okay. Do I have in total 1 hour or 1 hour and a half?
1 hour plus something. Yeah.
1 hour plus something. Okay. Then I will probably. Yeah. This is actually deal for me. Now I turn to open systems. Open quantum systems are systems that interact with the environment. An honest way to deal with them is...
I'm sorry,
Yeah.
by now you just explained to us that in this XX system, some Heisenberg equations
Can be solved
can be solved explicitly.
Right.
Without any particular explanation, why those equations,
Exactly.
what is good out of that.
Exactly.
Did something similar happens when we have like not a single operator, but like sum of two such operators with gap between them?
Good question. No, the life is much more complicated in these things, because when they evolve, they will collide, and then complex things happen when they collide. Okay. Open systems. From the formal point of view, open quantum systems I'm going to discuss are described by the Lindblad equation, and I will, again, there is a Schrödinger and Heisenberg picture of open system dynamics, and to save time, I'll just write down the Lindblad equation in the Heisenberg picture, and it goes as follows. The first term is just conventional Heisenberg equation, and then we have a super operator that is called dissipator. And there is some or some set of indices. Okay. This is an anti-commutator, and to make the things simpler, I'll tell you that I'm going to consider only unitary L's, and then this is 1. The anti-commutator is just the operator itself, and it simplifies just to OT.
What is the physical meaning of this equation?
let me give you an example, and in this example I will give the physical meaning. Okay, I'm not prepared to. So there is a deep and extensive theory of when quantum system plus reservoir can be reduced to an open quantum system under what conditions. Let me give you an example. Open physics model. The Hamiltonian is just the Hamiltonian I have already introduced, and these Lj's, now I will take index J is square root of gamma sigma z j, and this sum goes from 1 to n. This particular
It's not unitary, yeah?
is unitary.
It's unitary.
I mean, it's unitary up to a constant. Okay. Right. Now, this particular open system is an approximation to the following Hamiltonian. Maybe an approximation to the following Hamiltonian. This is the Hamiltonian of the XX model, and then we add an interaction between spins and bosonic bath. This is sum over J and over bosonic modes K, and here are some coupling constants. K, and also there is a bosonic reservoir.
I do not understand, Eric. So the sum over G and K separates, or what?
Right, it separates. So we
it's
have
interaction of total projection, total spin Z projection with what?
with a bosonic path. So it's, I mean, it's not essential that it separates. I put right here coefficients that are dependent both on the spin side and on the bosonic mode. So under certain assumptions, the main assumption is the smallness of these couples. Another assumption is that initially the bosonic bath is at high temperature. With certain accuracy, the dynamics of this Hamiltonian system can be described by that Lindblad equation. Okay?
But for this Hamiltonian, we can write usual Heisenberg equation, right?
Right.
And if we exclude bosonic variables, we obtain the equation which we wrote previously.
It's not easy to.
Is this the case?
No, it's not easy to exclude bosonic variables here. So it's not.
It's quadratic in oscillators. In principle, you can just by Gaussian integration exclude them. That's what you mean, Anton?
Yeah.
No, but then you get.
You get something terrible and non-local.
Exactly.
And but you say that when if these couples are small, or somehow
you mean that
it just in a special way, then out of that we probably can get something.
Right. I agree that this is one of the ways one can get this Lindblad equation from this Hamiltonian. I mean, it's not essential that the bath is non-interactive, but don't divert me from my main line. I'm not an expert in.
Хотим хоть что-нибудь понять просто.
No, I'm not an expert in deriving this Lindblad equation from the underlying Hamiltonians. I know that this particular Lindbladian can be derived from this particular Hamiltonian.
Lindblad is just this equation, yeah?
Yes, this is Lindblad equation.
which year? Какого времени это все?
Hmm?
Какой год это вообще?
70s maybe. I'm not sure. And the
76, 1976.
70s. Okay. Now let's see how these these guys are called dissipators. Now how these dissipators would act on our ANs, BNs, and all other stuff. It is easy to see that they don't act actually on sigma z's, but they act on sigma x and sigma y's. If I denote this whole super operator as D calligraphic, then it's easy to see that, say, D AN is simply minus 4 gamma AN for n not equal to 0.
If you это если вы обозначите всю эту скобку D, действующая на ОТ, что ли?
Right. And also D acting on Bn is minus 4 gamma Bn. From this we see that our equations that here are modified in a very simple way. We simply subtract here 4 gamma xn. Let's keep these energies. Since this minus 4 gamma doesn't depend on n, our solution is simply our solution without any dissipation times e to power minus 4 gamma t. So we have obtained in a very simple way a solution of this open system problem from the solution of the closed system. But of course you may suspect some trick, and this indeed a special case, because here this coefficient doesn't depend on n. Now let me consider a different dissipator. This was XX model with sigma z dissipation. Now let me consider XX model with sigma xy dissipation. Now our L's are simply L j equal to square root of gamma sigma x j, and L n plus j is square root gamma sigma x sigma y j. So now we have two n dissipators. They are very similar. However,
the sum of j is in before it was from 1 to n, yeah?
right now you see this is not j, this is nu. We can have yes, as many dissipators as we like, and now we have two n dissipators. Okay, Now the analogs. Now this dissipator acts on these guys in a somewhat different way. It acts on sigma z's. So each of them acts on sigma z's, and sigma x acts on sigma y's, sigma y acts on sigma x. So in the end, we get something like here we get absolute value of n. And this equation now gets the absolute value of n. And now these three could not work, but instead something really interesting happens. If this gamma were imaginary, then this equation would be an equation of a particle hopping on a line with a linear electric field. And as it is known that such hop problem features localization. It turns out that when gamma is real, this is now not, it doesn't correspond to any Hamiltonian problem, but still there is localization. And the solutions can be written in the form S and T, sum E there is an integer index x. It is integer. Let me write. Here goes x m. Here goes c n x. So don't be scared. These c's are eigenvectors of the matrix of the linear system. These chi's are eigenvectors of the inverse matrix. These lambdas are simply the eigenvalues. And
There is also sum over m.
there is also sum over
These are the highest.
sum over m. Right. I don't like this formula. Maybe something is wrong with it. No, it's okay. Now the point is, if this there were no modulus, then these size and highs would be just Bessel functions of integer order. Since there is module, this is not the case. However, at large n and m, there are indeed Bessel functions, and these Bessel functions have nothing to do with Bessel functions that we obtained earlier as functions of time. This psi n of x is something like j n minus x minus oi sine of x divided by gamma. And this, if here show this as a function of x, we will see that these are points, we'll get some points that are localized at x equal to n, and they're actually exponentially localized. This means that our operator in this
didn't get any. So you say that here psi is Bessel function.
It's approximately Bessel function.
Okay, approximately. But we have another function, I don't know how it is called, x
Chi.
high.
It is also approximately Bessel function.
So now you say how do you see that anything is localized? So what is on this picture?
The Bessel function as a function of its order is exponentially localized near zero for a fixed. So its argument is fixed up to this sign, okay. And it is exponentially localized. That's what I'm trying to say.
Ну, у вас там сумма, поэтому их суть, да?
Да.
Говорит, что из этой суммы остается одно слагаемое.
Ну не одно слагаемое.
Ну, там почти, ну там было
Few,
одно
few.
слагаемое.
Yes.
Ну, то есть это, тогда у вас эта матрица, которая до этого была какая-то общая, теперь становится там матрицей ранга 1, предположим. И что? Чего от этого всего хорошего происходит?
What I want to, so my message in the first part of the talk was that this Heisenberg operator is expanded in the subspace of operators which is linear in the system size. It is much smaller than the whole space of operators. Now the situation is even better. It is expanded in just few Schrödinger operators, not even extensive in the system size. That's the point. Now I am done with my.
Here, those few operators are just the sum over m of this high with x, yeah?
Right.
А лямбда от x она больше или меньше нуля будет? То есть она растет с t или падает?
Какая лямбда от x?
Ну вот там в какой степени это лямбда, да? Это там
Лямбда.
Yeah, it's negative.
негатив.
Right.
Бывает экспоненциально.
So I'm done with my linear part of the talk. Now I'll just, since there were questions about that, I will make a remark on this point. So we have seen that there are basically two cases. If some operator is a kernel of the of the dissipation superoperator, so if we have d over n equal to 0, then now let me say in a different way. If there is no non-zero operator such that d acting on O gives 0, then we observe localization in the operator space. And we believe that this is actually a generic case, and this observation extends to non-integral systems. If there is a set of operators such that d acting on O n equals to 0, then there is no localization. However, the operator expands in the operator space mostly over this subset. That's what we get from this integral.
Когда вы
Example?
говорите локализация, это локализация по кому?
This localization in the space of operators. What means?
What does it mean? What means this space?
It means well, in this. So if you have a Hilbert space of n spins, then you have a linear space of 4 to power n operators, linear operators, and acting in this space. In general, one would expect that a Heisenberg operator will spread over all these operators during the evolution. This is not the case for integral models, and we believe this is not the case for dissipative models in general.
типа, говорите, что это как в интегрируемости, когда что-то вот на каком-то маленьком кусочке остается.
And what are these operators in kernel in XY case?
This depends on dissipator. If the dissipator is sigma z, then, for example, any operator constructed of sigma z's is in this kernel. Say sigma z 1, sigma z 10.
Yes, but such operators doesn't show in our picture, yes?
Exactly, but this is just, a speculation about non-integral case.
See, and if dissipation is xy, we have equalization, so in our operators like x is a's, b's, etc., we have some of them which are in kernel, yes?
No, I believe there is no operator which is in kernel.
But we see localization.
Yes, we do. If there is no operators in the kernel, we do see the localization.
Okay.
If there are, the localization can be broken, the operator can spread over this kernel without localization. Okay, now I'm done and the time is over, so if you have any specific questions about this
Maybe
branch.
some algebraic explanation, because usually
yeah.
this set of distinguished operators can come from some algebraic reasons.
Yeah, exactly. These ANs and actually GNs form Zagreb algebra, and let me write down the structure of this algebra. It is a real algebra n minus m gn am equal to 2 n plus n minus 2 a n minus m and g's with different indices commute. A good thing with this algebra is that there are different representations of this algebra.
So G's with different indices just commute, yeah?
Yes, they just commute.
And this is a Lie algebra.
This is a Lie algebra.
Совпадающие. Кто с кем совпадающий?
Через совпадающие элементы тоже нужно.
Ну, если с разным, со всеми, то да. А что это за алгебра Lie такая?
What do you mean by?
В какую-нибудь классификацию попадает?
I'm not. I don't know. What do I know? What I know about this algebra is that it has representations other than XX or Heisenberg model, and these representations are n-state Potts models. They are integrable, but they are not free harmonic models. They are integrable by beta ansatz. And what is good with this method is that actually the way we obtain the Heisenberg equation is purely algebraic. And as soon as we get a solution for the Heisenberg operator in one model, we get it in all models. So it extends to any n-state Potts model. So the formula I have already written. Yeah. Well, anyway, when you get the solution in form of xm, here goes some functions of t. This solution is valid for any n-state plots model. However, if you want to calculate the expectation value for t in some initial state, and these functions are the same, but for each particular model, you need to calculate these expectation values from the outset. So solving the simple XX model gives half of the solution for any n-state plots model. That's the point.
What is the Hamiltonian of the plots model?
I can write Hamiltonian of three-state plots model, if you wish. I can actually write Hamiltonian of a generic plots model, but in somewhat formal way. This is there is a whole zoo of these plots models, and not an expert in. These particular plots models go under the name of chiral plots models. The Hamiltonian is equal to something like tau j1 minus omega c a plus b some sigma c. This a and b are coefficients. These tau and sigmas are matrices with the following algebra. N minus 1, 1.
Are they n by n matrices?
Right, they are n by n matrices. And there is this paraharmonic commutation relation.
But you write cube, so it is n-state model or
And
three-state.
sorry, it's n-state, right. Yeah. So I have explicit forms of these matrices for three-state, if you wish. Tau is something like 1 is the diagonal matrix with omegas on the diagonal, and sigma is something like L0, O, 1, 1,
And it is not free harmonic model.
It's not.
Right, for n greater than 2.
Yeah, exactly. Yeah, and omega n is a root of Q. Okay, more questions?
I didn't quite understand why, when we in the finite volume case, the boundary condition, like when little n is greater than big n, are different from the case where we have like operators, get different operators, and they are crashing. Because it essentially happens the same.
Yeah. I don't, well, we better discuss this.
Sigma in this formula, does it have index J?
Yes. I mean,
It is J and J plus 1, right?
yeah.
Okay.
Exactly. A short answer is that this is a good type of collision when you have a same string wind it over the whole. But not all collisions are of this type.